Okay, good. So, although we delayed for a week, I will now give the talk on the cloaking stuff, the question that we were going to discuss last time. So this is based on a couple of papers and actually a pretty extensive line of research. The first time I was introduced to this was a talk I attended my sophomore year at MIT by Professor Stephen Johnson, who was working on this, and I thought it was pretty cool. So I've tried to synthesize some of the research in this direction in this talk and make it a bit more accessible. And I now realize that I have been putting 2018 on all of my dates, which is not correct. But ignore that for the moment. So what is the question we're trying to solve? I'm going to draw a lot of pictures or put a lot of pictures like this on slides. And the meaning of a picture like this, you should interpret this as sort of a two-dimensional slice. So this is like a cut of some three-dimensional object where we're always going to consider, for simplicity, an object in the interior here, which is the thing that we want to hide. So there's always some circular object, although of course you can change the shape of the object, it just makes the problem slightly more complicated. But there's always going to be some object and then some cloaking region that we have. So in this case, the cloak itself, the invisibility cloak, so to speak, that we want to build is this sort of larger sphere, and inside of that sphere we would like to hide some circular object. And then the color, sort of the plot that I'm showing here, is supposed to represent the amplitude of some electromagnetic wave, some light. Some observer is scattering light off of our object. And I'll explain that in more detail shortly. But let me just contrast what usually happens in that scenario with no cloaking with what we would like to do. So usually, if this object is just sitting here and it's some ordinary object made of everyday materials, when you send in some light rays, so the alternating blue and red here represent just some oscillating waves, some light, some visible light, usually that light interacts with an object in a fairly obvious way. So there's a shadow behind the object, which I'm circling here, where no light passes through because it was somehow blocked, and there's some reflection. So you can kind of see here the incoming wave has these sorts of kind of rays emanating outward backscattering from the object. And this is what an observer uses to see the object, to image what we're trying to hide. So this is what happens usually. The problem we're trying to solve is to ask the question, can you design some material in the cloaking region? So can you change the properties of the object, or the region surrounding our object, so that when an incoming light wave bounces off of this thing, at some sufficiently large region away from the object, it looks as though the thing weren't there. So for instance, you could see here that somehow, in this case, the cloaking has bent the incoming light rays around the object in such a way that if you were standing behind it, you would not be able to tell that there was an object between you and the light source, right? These outcoming light waves look very much like the incoming ones. So it's effectively as though the object had not existed. And I mean, there's a little bit of backscattering here, but that would also, I mean, when you get far enough away, it's supposed to be minimized for, somehow a perfect cloak. So anyway, that's the problem we're trying to solve. So the topic of today's talk is, can you design such an invisibility cloak, an object with the property that light passes around it more or less unaffected? Good, so that's the question. So to avoid this becoming me speaking continuously for 40 minutes, I'll ask you to brainstorm and contribute some ideas. So just to brainstorm, because our cloak involves some material with the property that it manipulates light or bends light rays around it in some sense, I will ask you for suggestions. Can you think of other less exotic examples, things that you're familiar with just from everyday experience, that manipulate the propagation of light in some way? Any ideas?
All right, if I go first.
Mm-hmm.
The first thing that comes to mind is like gas particles in the sky.
Yeah, so good. So basically the atmosphere scatters, this is why sunsets look nice, right? Atmosphere scatters light. This is why the sky is blue. This is why at sunset, because of diffraction of the light through the atmosphere, the sunset looks red, and so forth. Good, very nice example. Other examples?
You could just consider lenses.
Yeah, very nice. So a lens can focus light, either the lens in your eye or the lens in a camera, or there can be diverging lenses. So this basically just causes light rays to get either focused together or spread apart. Good. Other examples?
Mirrors.
Yeah, very nice. So a mirror is kind of a more severe example of a lens, where a lens just sort of bends the light in some sense. A mirror actually reflects it. Good. Yeah, I think this is a pretty reasonable collection of examples. I think they're more or less the ones that I included in my quote-unquote solution. So I think the one that people most commonly think of are lenses, as you say. So a lens could, for example, focus light through some focal point, which could be, for instance, in the retina of your eye, if you like. Often people think of prisms, where a prism sort of changes sort of the angle of propagation of light in some way described by Snell's law, for instance, you may have heard of. So this is actually rather similar to what happens in the atmosphere, although in a less severe way. Mirrors, as you say, reflect light. And one example that I like very much, although it's not really relevant here, is you may notice if you're walking around on the street and there's like a thin film of oil on the street, that it always has this beautiful rainbow pattern, this thin film interference. And this is something you would study in a physics course on waves and optics, but this is really just due to light propagating through this thin film of oil, and sort of some of it gets reflected down and bounces back up, and some of it gets reflected directly back up, and these two different outgoing light rays interfere with one another in an interesting way to create these color patterns. So another example. But good. Okay, so this brainstorm is useful, I think, for listing examples of light manipulation, but all of these are fairly ordinary, and in order to create something which makes an object appear invisible, we need a much more exotic or more severe form of control over the propagation of light, which will be quite different, involve different physics from all four of these examples. And that is what I hope to tell you about for the...
Oh, I forgot to say, you could use something incredibly heavy.
Something heavy. Oh, you mean like put a black hole that bends light around it? Yes. Oh, I don't know why I find that so funny, but yes, yeah, you could basically. I mean, this is like the Eddington experiment that verified GR, that like light bends around the sun, so you can see behind the sun because it bends light around it. So yeah, sure, you could build a invisibility cloak by making your cloak a black hole, but you're going to have bigger problems if you're carrying around a black hole to hide yourself. Good, I like that.
There's too much light in this room. Just put a black hole in it.
It solves all of your problems in a very real sense, in the same way that suicide solves all of your problems.
I mean, yeah, in a sense, if you put a black hole in a room, your problems are about to become a very small matter of fact.
Yeah, it really puts things in perspective when you're fighting with a black hole. Good. Okay, well, I'll jump right to the punchline and then try to explain what I say in the punchline and convince you that this is actually true. So the short version is that yes, although this sounds like it may be a fantasy, it is actually true. So physically, in principle, there's nothing stopping you from designing a material that has this property, that bends light around it in a way that makes it invisible in the same way that, say, Harry Potter's invisibility cloak or something works. So it's totally physically possible. And beyond possibility, it's something which has actually been demonstrated to a limited extent in practice. So in the third act of this talk, I'll tell you a little bit about the material science side, which is something I'm much less familiar with. And I'm kind of sad, actually, that Adam isn't sitting in, because Adam, as an engineer, has actually studied material science, so he could heckle me about my attempt to explain this in the last part. But I'll try to tell you a little bit at the end about how one actually builds a material with this property, which involves in a key way these so-called SRRs, or split ring resonators, which are roughly this sort of mesh of sort of circuit board-like, well, circuit board exactly, circuit boards with particular combinations of current loops that are going to generate electric and magnetic fields in a prescribed way, basically. Good, so that's what's coming. That's the answer we're trying to understand. So that's the answer. To understand why this is true and how you design such a property, and really the reason why I'm interested in this question, this is actually closely related to certain mathematical techniques in theoretical physics and string theory. so to build this thing, we're going to need to use some mathematics using a so-called coordinate transformation. So if you've taken, trigonometry, this is an example of a coordinate transformation. Is just going from Cartesian to polar coordinates, or perhaps more faithfully, if you've taken calculus, a u substitution where you evaluate an integral by changing variables from x to u of x. These are all examples of coordinate transformations, but if you take multivariable calculus, there's kind of a, totally general case where you change from, say, two coordinates x and y to two new coordinates u and v. And that's what we're going to use, really, to find the properties that our cloak must satisfy. And in particular, we're going to choose that coordinate transformation so that the uncloaked object, the circle that we're trying to hide, the spherical object we're hiding inside our cloak, we're going to make it look like a circular object or hole with a different radius. So for instance, if you're trying to hide a ball with radius 1 meter, we're going to write down a coordinate transformation that lets us make that ball look like a smaller ball of radius rho, where rho is any number we like. So we could choose rho to be, say, 1 nanometer. So you can make your 1 meter size ball you're trying to hide look like a 1 nanometer size ball, which no one could actually see. And that's the sense in which we mean that we've cloaked the object. We've made it look like some much smaller spherical object. Good. Okay. So the plan, this is like the sort of introduction or something, but I'll try to walk you through first the equations of electromagnetism, the things that you use to show that this is possible in principle. Then some properties of materials like anisotropy, which will be key to designing a cloak that actually makes things look invisible. And in the last part, I'll summarize some actual work where people did this with split ring resonators and tell you, sort of how it's done in practice. But good. Okay, so that's the introduction. So I should pause here and say if there are death threats that have emerged already or comments you would like to make, this is a good time for those.
Apparently, no one believes in death threats.
Yeah, I have a hard time getting death threats in these talks. It's really rather disappointing, actually.
I mean, if I'm trying to think of one, it's just not going to be creative. If you give me a little, I could probably figure it.
I mean, creative death threats are the more, useful ones to have. Like, if you tell me, I'm going to stab you to death, well, that's fine. But if you tell me that you're going to, like, strip me naked and tie me to a boat and cover my body with honey and then let loose a bunch of bees that are going to eat me alive, which I think people actually did back in, historical times or something, then I would be more impressed. But, okay, anyway, well, if no one's going to kill me or draw and quarter me or something.
I was just going to expose you to bad puns.
Yeah, I mean, I could die from bad puns as well. That's one
fate
possible.
worse than death.
Yeah, it's a form of execution. Good. Okay. Well, onward then to some electromagnetism, which might be especially of interest to Logan since he's studying this now for his independent study course. But so why do we need to understand electromagnetism for this problem? So again, what we're trying to do is take some spherical object, which I've rendered here, in 3 dimensions, and then build a larger spherical cloak with the property that sort of light rays bend around it in a way that is unobservable if you're sufficiently far away. So in order to understand mathematically what's going on with this problem, we need to basically understand how these light rays behave in 2 different places. So place 1, out here, is in empty air outside the cloak, so just free light propagation in the atmosphere. And then in region 2, inside the cloak, that's the more important piece. We have to understand what laws govern the motion of light within the cloak and how we can sort of engineer or change those laws to suit our purposes. So good, that's the motivation. First, what is electromagnetism and what is light? So if you take a college course in E&M or Physics 2, you'll spend, a semester of your life doing this, but the short version is that the entire theory of electromagnetism is simply a way of assigning 2 arrows to every point in space. So if you just imagine filling all of space, attached to every single point in space, we have two different little arrows that have, some direction and some length, and one of those arrows is called the electric field, which I write with E, and one of those is called the magnetic field, which is written with B for reasons which I don't understand, B for magnetic apparently. And these can change, so you can have different lengths of arrows. Maybe in some places the arrows are 0, but there's still 2 of these arrows at every point of space, filling all of space forever. This is what we call a vector field. So it's a very complicated sounding word for a very simple idea of simply attaching 2 vectors to every point in space. Okay, good. So suppose we've done that. You might ask, okay, are there rules or something governing these arrows or something? And the answer is yes. So, for instance, you may be familiar with the idea of a battery, or something which creates a potential difference in the electric field. So, if you have a battery or some capacitor or something, some apparatus that wants to generate an electric field, we sometimes describe this with something called an electric potential. So in the following slides, I will use the letter U for this potential. In equations, we write this as the electric field arrows are minus this upside down triangle acting on U. All that equation means is that the electric field points from high potential energy to low potential energy. So the triangle just means the direction of change, and the minus sign means we're going from high to low rather than low to high. So if you had, say, a bunch of positive charges up here and negative charges down here, you could show using the equations of electromagnetism that up here is a high potential energy surface and down here is a low potential energy surface. So all of the electric field lines point downwards. So they point from the high to the low. And in the scenario I'm describing here, there's no magnetic field. So all of the magnetic field arrows are 0. Okay, so this is one way of describing it. So we have electric field, and they point in the direction in which this other thing U, this potential, decreases. Okay, fine. You might ask, how does this help us? We're trying to understand visible light. We're trying to understand seeing an object and hiding it. So it's important to understand what visible light is. When you look at something, what are you actually seeing? Visible light, as Maxwell learned in the 1800s already, visible light is just a certain pattern of propagation in those arrows. So a light wave is simply a pattern where the electric field arrows, here shown in red, and the magnetic field arrows, here shown in green, travel in space in a particular way. And the way is really simply just changing both the length of the arrows and the direction. So as you move in space, the electric field arrows are pointing up, they increase to some maximum, then they decrease, and then start pointing in the opposite direction, and continue. The magnetic fields point in a perpendicular direction, and similarly oscillate, from here pointing to the left, and here pointing to the right on screen, and back to the left, and so forth. And this thing changes both in space and time. So if you wait maybe 1 second, then this entire picture sort of translates to the right on screen by some distance. So this is all light is. When you look at something, there's simply a pattern of oscillating arrows in space that hits your eye, and that data is interpreted as some sort of picture by your brain. That's it. That's all light is. Okay, so as I said before, we have to describe the equations of electromagnetism in 2 areas, the free area outside the cloak and the area inside the cloak. So outside the cloak, now we're basically done. I've effectively told you everything you need to know about light propagation in empty space. Basically, the electric field at least. From now on, really, the magnetic field is less relevant, so I'll just focus on the electric field, so you can just think of 1 arrow per point in space. The laws of electromagnetism, as written by Maxwell's equations, basically just tell you that in empty space, the electric field satisfies something called the wave equation. So again, if you've taken trigonometry and know what these sort of oscillations or sine and cosine waves look like, here's one solution to the wave equation, and below is just basically the same picture I've written before, where if you simply focus on the electric field, you can see that its amplitudes here oscillate by a sine or cosine. So this is basically the entire answer to the question of how the light behaves in free space, this oscillation. So this is somewhat less interesting. We have no control over this. This is basically dictated to us by Maxwell and by just the laws of physics in vacuum. So there's nothing we can do about this. The only control that we have is within the cloak. So we'd like to move towards understanding how the laws of electromagnetism are modified inside materials, like a cloak. Good. So forget the empty space. Totally, let's ignore now what happens to the light outside the cloak. Now we're going to think about what happens when these electric field arrows move within some material. And our material, like everything else, is going to be made up out of matter. And matter has charge, like the electron, which carries negative charge. So the punchline is that when an electric field exists within matter, the charges which make up that matter are going to move. So, as it turns out, almost by definition, a positive charge, like a proton, is going to move in the same direction as this electric field arrow, which, the direction that the arrow points near the charge basically just tells you the direction that charge is going to move. And negative charge, like an electron, is going to move in the opposite direction. So if the electric field points this way, then this charge itself moves in the opposite direction with some velocity v or something. So this just describes the way that charge interacts with electric and magnetic, well, just electric fields here. So if there is an electric field which is non-zero present in some material, the charges will move, and the aggregate effect of charges moving in some direction is something called current. So for the rest of the talk, I'll ask you to think of a second arrow. So imagine another different arrow besides the electric field at each point inside a material, which is telling you the direction that the charges are moving in aggregate, right? So these things can be bouncing around, but as I've drawn it here, the current arrow, which I'll usually write with something like a capital J with an arrow over it, that current arrow tells you the net direction of charge near that point. So J can be different from the electric field. For instance, if all of these charges are negative, if these are electrons which are moving, then here the fact that they're all moving to the right means that probably the electric field in this material is pointing to the left. So these arrows are totally different. Good. Okay, two arrows. One, the direction charges are moving. Second, the direction of the field. Are there more thoughts or death threats on this? Because I've now covered basically half of an undergraduate physics course in a couple of slides, so it should be confusing.
Okay, so about those death threats.
Good.
I was bored yesterday and bought this book and completely forgot about it. And it's just full of a bunch of different deaths and theories on afterlife. And so I flipped to a random page. And if you want, I could read one about Viking burials.
I'm very
interested. And if you want, if you want, I could put it in the Discord if you want to keep the YouTube PG. Because it's Viking ship burials.
I don't really care about PG-ness, but I would like it on Discord as well, just for my personal enlightenment later.
Alright, so here's this short paragraph. I'll throw it into Discord then, and you can continue with your talk.
Good. I think I'm going to take a break from electromagnetism to read this after you post it, though. Wait, is it going in the DM or in the channel?
Of all the things you could choose to take a break for.
I'll probably put it in the channel quick. What chat should I throw it in?
General's fine. I want everyone to see this.
Alright. What page is it on again? There it is.
It'll probably take you a second to type that.
Yeah, just keep going. I'll tell you when it's up.
Okay, well, good. Let's see. I think there's a bit more that we have to say about this motion of charges. So maybe I'll introduce this next part, and I think there's a question for you guys, and then I'll read your Viking burial. Good. So one equation we'll use repeatedly within the cloak is conservation of electric charge. So there's a very deep statement about physics, which really, I mean, conservation of charge is really just a consequence of, the fact that if you rotate by some angle in the plane and then rotate by negative of that angle, you get back to where you started. So if you take quantum field theory, you'll see why those rotations tell you that electric charge is conserved. But for now, just trust me that electric charge cannot be created or destroyed. So if you have some region R in the plane, and we have these little arrows J that are telling us the direction that the charge is moving, the current, if you will, at each of those points. And you imagine sort of adding up the total contributions from that current flow into the region and out of the region. The claim is that that total amount must be zero. Or in other words, the total amount of charge within the region R should not change, assuming the charge cannot pile up within this region, which is something we will assume about our cloak, simply because charges repel, so it's not favorable for a lot of, say, negative electric charge to pile up in here, since then those charges would repel and try to move apart from one another. So the claim is that for any fixed region, if you simply add up all of the incoming charge and subtract all of the outgoing charge from that region, you should get zero. So this is conservation of charge. Okay, fine, it's a simplistic sort of statement, but this is something which ties in beautifully with a sort of concept that one would study in a multivariable calculus course, which is called the divergence. So I'll try to just explain this to you in pictures. Divergence just tells you exactly what I described on the previous slide, namely, if you have a small region surrounding some point, divergence tells you whether the net flow of some arrows into that region is positive or negative. So there's three cases, basically. We write divergence with this symbol with an upside down arrow and then a dot, and then the vector v. Different from what we saw before, that just had an upside down arrow with no dot. But this thing on the left is called the divergence. If the divergence is negative, so we say that charge is not diverging from this point, it's converging at this point, which means the arrows are pointing inward. So that's negative divergence. In the middle picture in green, if the divergence is positive, that means that charge is diverging from this point. So as you can see in the picture, the arrows are all pointing outward, so charge is diverging. And in the third picture in blue on the right, all of the charge is sort of moving with the same speed at different points. So this means that the amount of charge entering our little circle is the same as the amount of charge leaving. So there is no charge diverging, or the divergence is zero. In other words, we say that this configuration is divergence-less. So re-expressing what I said on the previous slide, that the amount of charge should be conserved, so the amount of charge entering or leaving a region should be zero, we want this third case on the right. So we want the current to be divergence-less, so the charge does not pile up or leave a region or something, so all of the charge escapes somehow. Okay, so this is our conservation equation, as it's called, conservation of charge. Okay, so now a question for you to test this idea of divergence. So in this picture below, notice all of the arrows are the same length. So in this picture, rather than using the length of the arrow to tell you the speed of charges near a point, we use the color of the arrows. So in this picture, blue means that the charges are moving very fast near that region, and green means that they're moving less fast. So for instance, if I look at a region way out here on the left side and draw a very big circle, I would say that here there's a net amount of charge leaving this big circled region on the left because charge is moving in very slowly, green arrows at the top, but charge is moving out faster, these bluer arrows at the bottom. So I would say there's a net charge leaving this area, so I would say that it's a source, basically. Charge is spilling out. Okay, so that's what I mean by a source or a sink. And now a question for you in the red circled region here, using the same sort of analysis, is charge building up or spilling out of this region, or neither? Conservation of charge. going to eat some cheese while you think.
Looks like it's building up.
Yeah, I think so. While I chew, why don't you explain so I don't have to talk while chewing?
Alright, so at the bottom of the circle, it looks like the arrows are more blue than the arrows that are leaving the circle.
Mhm.
So charges are moving in quicker as they enter the circle and slower as they leave, so they'd be building up a little bit.
Yeah, that sounds right to me. So, indeed, charges are moving in quickly at the bottom, slowly at the top. So I would say that here, I would write this in equations as, the divergence or something is negative because it's not diverging. In fact, it's converging at this point. Charge is building up inside, right? So this is a sink. Charge is piling up here. Good. So this is the configuration I've shown here is what we don't want to happen for our charges, right? Because we do not want charge to pile up at any one place, since it seems to violate charge conservation. Okay, Logan's computer took a dump, but I thought that was going to be my Viking burial or something. Good. Okay. Wait, do we have... Are the other two people here, or did we lose people? No one.
I'm still here.
Takumi
Your
said...
Viking burial is ready.
Ah, okay, good. In the 10th century.
You might need a double take. It takes a while to fully process the entire set of events.
A dramatic reading. In the 10th century, Ahmad ibn Fidlan, a famous Arab Muslim writer and traveler, wrote of the funeral of a Scandinavian chieftain whose female slave volunteered to join him in the afterlife. After being given intoxicants, she had sex with many of the men, who then placed her at the side of the corpse in the funeral ship and raped her. She was then strangled and stabbed by an old woman called Angel of Death, and the ship was set afire. I don't know how else to react to that besides wow. Good. Well, thank you for that. It's the best death threat I've received during a talk.
You're welcome.
Okay, well, we lost Logan, but I guess he can watch the video later or something. But okay, good. So we have this notion of conservation of charge expressed by the divergence, and we're going to model our cloak as a conductor. So there's another rule that if you have some conducting surface, if you think of this as a metal, the electric field lines should end. So by field lines, I mean if you just take all of the arrows, remember the electric field is a collection of arrows at every point in space. If you sort of connect those arrows together into lines, you get these electric field lines, and they are supposed to end on metal surfaces or conducting surfaces like our cloak. So as we'll see in the remaining part, the last 10 slides, this sort of electric field lines ending on a conductor is the game that we're going to play with someone who's trying to see the object that we're hiding. So the observer, in some sense, picks some input current, which we write with the letter G, which is a configuration of electric field lines outside the cloak. So he gets to pick those currents, and then he sees the reaction, basically. So he gets to see what happens when he chooses those input currents applied to the cloak. And we're going to try to design our cloak so that even if he gets to choose whatever current he likes, he cannot extract any information about what's inside of it. That's the invisibility part.
So, what did I miss in the past 5 minutes?
You missed a woman getting raped and a ship set afire. You missed. Did you see the challenge? What was the last slide that you were?
I started seeing it, and then my computer just died.
It took a dump, as you say.
What did you say?
So in this challenge, Takumi explained to us that in the circled region, charge would be piling up because all of these blue arrows represent fast motion of charges. So here, charges are moving into the region very fast, but green arrows are more slow motion, so charges are leaving the region very slowly, but entering very fast, so charge was piling up inside this region. So that was the answer Takumi gave, which was correct, so this is something we don't want within our cloak, conservation of charge. And then I spoke a little bit about how electric field lines end on conducting surfaces. So by electric field lines, I just mean, the electric field is an arrow at every place, connect all of those arrows to make some lines, and as it turns out, those lines should end on these conducting surfaces. So this is the sort of surface of our cloak that we'll use in the remaining 10 slides.
Okay.
Good. Okay, questions on this or other Viking? Yeah, Alex is unhappy with your Viking death threats, but good. Okay, so questions on this stuff before I tell you about why we need some kinky shit going on inside of our cloak in order to get invisibility.
So I've got a question about how you defined current before.
Good, yeah.
So we actually went over current maybe 1 or 2 weeks ago in physics 2, and my professor explained it as the movement of positive charge instead of negative charge.
Yes. Absolutely. Yeah, there's a choice of convention here. So here, yeah, the convention that people typically use is current is flow of positive charge. Yes. So this is a total historical accident. Basically that, I mean, if you have a circuit, you should really think of the things that are moving in a circuit when you have some battery here. So if you have some battery that applies a voltage, the things that are actually moving are electrons, right? So if there's a current, say J, which is moving, I don't know, clockwise or something in this circuit, the electrons are actually moving in the opposite direction. So the electrons are moving this way because electrons are negatively charged. And again, this is just a historical accident that electrons were kind of discovered first. You could blame Ben Franklin or whoever. So indeed, yeah, current will be the flow of positive charge. So if these guys, these Q minuses that are moving here, are electrons and they're all moving to the right, then we would define current here, J, as going in the opposite direction. You're totally right. I'm sort of glossing over this point because for the purpose that we're considering here, which is just whether the charge is conserved, whether the divergence vanishes over some region, it doesn't matter whether this is positive or negative because negative 0 is still 0. But yes, I agree. If you're taking a physics course and need to get the correct sign in your answer for the current, it is very much important that current is flow of positive charge. So if electrons are moving, current is pointing the other way. Yeah, good. That's also related to the fact that here I said if the electric field were pointing to the left, then all of the electrons, which are negatively charged, would move the other way, to the right. So the statement you just said is really just the statement that if the electric field is pointing to the left, the current should also point to the left, even though the direction that the physical charges are moving in is to the right. Because we flip the sign of this motion because all the charges are negative. Good, good. Does that make sense? Is that what you were getting at?
Yeah, thanks.
Good. Other questions or death threats?
9.
9 questions. Interesting. I'm kidding, of course. Okay. So with that caveat about the sign of the current, let's talk about what we need for cloaking. Okay, so first I'll contrast what happens in an ordinary material. So if you turn on an electric field in a wire, as we were just describing, the electrons are negatively charged, so they're going to they basically move opposite the direction of the electric field. So if the electric field again is pointing to the left in this picture, the electric fields point to the left, the electrons are going to move in a fairly random direction, but with some net drift to the right. So these electrons are all bouncing around in some sort of Brownian motion or whatever, some random walk, but this random walk has some bias, so that on average they are moving a little bit to the right. So as Takumi pointed out, if the electrons, which are negatively charged, are moving a bit to the right, then on average we have a current pointing to the left, current J. So we express the statement with this equation that tells you that if you turn on an electric field E, then you get a current J which points in the same direction as your electric field E, although the length of that arrow could be different than the length of your electric field arrow. So to express that the lengths of these arrows can be different, we put in this proportionality constant, this number sigma, which is called the conductivity. So if sigma is very small, then you apply a huge electric field, conductivity. You apply a huge electric field times a small number and get a very small current. If conductivity is huge, as in a superconductor, then you apply just a small electric field and get a huge current. Good, so this is how ordinary materials work, but we'll see that this isn't actually good enough. So by ordinary, I should be a bit more precise. By ordinary, I mean a material that is isotropic. So what is isotropic? Isotropic is this material on the right, where there's sort of a random assortment of maybe some nuclei or particles or whatever that are completely uniformly distributed with no preference in direction. So in an isotropic material, there is no distinction between different directions. All directions are treated the same democratically. We're going to contrast that with an anisotropic material. An anisotropic material has a preferred direction. So if you're sitting at a point in this anisotropic material, say this point here, two directions look very different to you, because if you move to the right, then you are moving between these black regions, which could be, say, holes or grain. If you imagine this as a piece of wood that has some grain in it, that, the grain picks out a particular direction. If I move to the right, I'm moving between black, these black squares. If I move down, I stay within these sort of gray squares or something. So here we've explicitly picked out one direction as being different from another. Moving to the right is different from moving downwards. So this anisotropic material has the property that currents will respond differently to electric fields applied in some directions compared to others. So we'll see that this is really unusual, but it's actually exactly the property that we will need for cloaking. So, ooh, I heard a noise. Is there a question?
Not quite a question, but I think there's an optical illusion going on with those shapes.
An optical illusion? Why does this look like weird to your eyes?
It is genuinely making my eyes hurt, and it looks like it's wobbling.
That was not my intention. Maybe I should advance from this slide so that you don't have a seizure. Good. Okay, so why am I bringing up isotropic versus anisotropic? Well, the isotropic materials, the ones where all the directions look the same, like ordinary matter, in those materials, the current always points in the same direction as the electric field, as we said. So J is sigma times the electric field arrow. And the problem with that is that if you write down the laws of electromagnetism, which I'll just try to summarize. I mean, don't get scared if you don't understand these equations. I'll just try to tell you in words what they mean. So this first equation, well, this upside down arrow times U is the electric field, roughly. So here this is sigma times the electric field, but we know that sigma times the electric field is the current J. So this top equation is telling you that upside down arrow dotted with J is 0. But as we saw in the previous act, that's just current conservation. So that's just telling you that the direction of motion of charges is divergence less. So there's no buildup of charges. So that's one equation. The second equation, this is basically that the electric field lines have to end on conductors. So this is something telling you about, roughly speaking, this is telling you about the perpendicular direction, sometimes called the normal direction, of the electric field on the boundary. So the problem is that these two equations will allow an observer to see what is inside the cloak if sigma is just a number. And worse yet, this will allow the observer to see what's inside the cloak even if sigma is a function. So if the conductivity can change between different points of the cloak, so it's a big number in some places in the cloak and a small number in other places, that's still enough that the observer can see basically what the conductivity is at every point inside the cloak simply by choosing what G, basically what light he's throwing at the cloak. So he can always image the cloak, as we say. The observer can always see inside the cloak, assuming he can apply whatever light to it that he wants, if this sigma always just tells you that the current points in the same direction as the electric field. So the observer can always measure this conductivity by applying some light, some electric field to the surface of our cloak. So that's bad news, because that means, if this were the end of the story, then you would just say, okay, invisibility is not possible, there's nothing you can do. But thankfully there's a way out. And the way out is simply to be a bit more creative. You could say, what if, instead of saying when you apply some electric field E, before what I was saying is that if you apply some electric field E, the current, or the direction of positive charge motion, will always point in the same direction as your electric field. So here's the isotropic case that I'm drawing in blue here, isotropic. You apply an electric field, the charges, the positive charges, always move in the same direction. You could imagine a somewhat more involved scenario where you apply some electric field and the current now points in a different direction. So that's what I've drawn here. If you apply an electric field which points to this, I don't know, 1, 1 or something in coordinates, and you get out a current which points in a different direction, say 2, 1. So this is different. This is not saying J equals sigma E, which was just telling you that the current is always going to point in the same direction as the electric field. This is now saying that the object sigma is not just changing the length of the arrow, it's also changing the direction of the arrow. That's something you could never get in an isotropic material, but you can get in an anisotropic material. You can change the direction because an anisotropic material treats some directions differently from other directions. So that's the point. And mathematically, the tool that you use to express the transformation of one arrow into an arrow with a different direction is something called a matrix. So you may have seen these in an algebra course, or you may not have because public school, but if you wanted to write down a matrix which did the transformation I showed you on the previous slide, that turns the arrow 1, 1 into the arrow 2, 1, you could write down a matrix of this form if you like. So this 1, 1, 0, 1. And the rules for these things is that to get the top component of the right side of this equation, you just do a sort of multiplying and adding procedure where you take this guy times this guy, 1 times 1 is 1, and you add this guy times this guy, 1 times 1 is 1 again, so 1 plus 1 gives you 2. And then to get the bottom guy, you take this thing, 0 times 1 is 0, plus 1 times 1 is 1, so you get a 1 down here. Okay, so that's fine. I mean, you can imagine putting different numbers in here, and then if you had, say, sigma xx, sigma xy, sigma yx, sigma yy, and you multiplied by some input electric field, say ex, ey, using those rules, you can get basically an arrow which points in whatever direction you like. Sigma xx ex plus sigma xy ey, and so on. So this is what we need to achieve cloaking effectively, to be able to move these arrows in whichever direction we like. Good. Okay. So I think I've set up basically all of the problem, and so in the last couple of slides, past the last 10 minutes basically, if we go for 1 hour, I'll just tell you how basically you find what that matrix has to be in order to cloak something, and then tell you how people have built it in practice. But good. Before that, any other stories about rape and arson of ships or other death threats? None. Radio silence. People do still exist though, right?
Yep.
Ah.
I see everyone is muted.
Still here.
Ah,
No, I don't exist.
people do not exist. Okay. Good. Okay. Well, 5 slides. So I'll try to wrap up. So, what have I tried to convince you of? I've tried to convince you that we need our conductivity to turn into a matrix. So, if you want to build an invisibility cloak, you need 2 things. 1, you need a way of calculating what that matrix has to be, and 2, you need a way to build a material with whatever conductivity matrix you want. Right. So, a recipe for cooking up a material with a given conductivity. So the solution to problem 1 is mathematical. That's the sort of thing that I'm interested in. To solve problem 1, what people have done in some of the papers that I sent out is to use a coordinate transformation. So by coordinate transformation, I just mean a way of changing, a point in the xy plane by some function. So for instance, this thing is supposed to take some point here and send it to some other point in the plane over here, for instance. And if you apply that to every point in the region, it's going to change the shape of your region. So here there's a transformation which changes a rectangle into this sort of circular wedge or something. So you apply some function, it moves you from the left to the right, or you can apply the inverse, which moves you from the right to the left. So that's the idea of a coordinate transformation. Why does that help us? Well, it helps us for the following reason. So if we go back to what we wanted to do, which is to basically take a cloak with some object that we want to hide that has a big radius, say r, like a meter or something, and we would like to make that look like a tiny, tiny object, with a radius rho that could be like a nanometer or something. That's what we would like our cloak to do, make our object look like it's very tiny. And as it turns out, in some papers, people proved that you can do this by making a coordinate transformation which sends the tiny ball, the radius 1 nanometer or whatever, the tiny ball, it maps that into the shape of the true object, which could be a big, 1 meter ball or whatever the actual shape of your object is. If it has a more complicated shape, you need a more complicated function. But the point is that if you have such a coordinate map, which we use the Greek letter phi for, then the equations of electromagnetism can be written in terms of this new variable v, which come from composing the electric field function, the electric potential function u that I wrote down before. You compose that with the inverse map of phi. Okay, so the details are a bit involved, but it's not super important. All that we need to know is that v is sort of a coordinate transformed electric potential. We get these new equations, which involve the v and also the conductivity matrix sigma. And then you simply ask, okay, what solution, what choice of the conductivity matrix sigma solves these equations? Or in other words, what choice of the conductivity matrix sigma makes these equations true so that light scattering off of our cloak makes it look like the object inside has this very small radius rho, which could be a nanometer or something. And the problem's not hard to solve. It's worked out in a couple pages in some of these papers, but you just write down the solution for the conductivity matrix, and it basically just involves some derivatives, some calculus techniques applied to our change of variables. So this is basically, some vector, some combination of derivatives of phi, and this is the transverse of that vector. So a vector times a transverse of a vector gives you a matrix, which is not especially important, but the point is that there's just some answer you can calculate if you know what the coordinate transformation is. So even if these details are very confusing, all you need to know is that the input to this, recipe was the coordinate transformation, and the output was the answer for sigma, the answer for the matrix that we need that cloaks the region. Good, so that's it. That's the math. That's the answer to question 1. Question 2 was, if I know what sigma has to be, which I do because of the previous slide, how do I build an object that has a conductivity matrix sigma that could be whatever I want it to be? And this is those split ring resonators. So if you study material science, you can see how engineers use these metamaterials, which are basically built from a mesh of circuit boards. These circuit boards, when an electric or magnetic field from, say, light impinges upon these, so we have some electric and magnetic fields impinging upon these, the circuit boards have some current that flow in response to that light, and the currents flowing within the circuit board generate their own electric and magnetic fields in response to the applied electric and magnetic field. So they're drawn here in the top. These blue arrows are the electric field lines generated in response to some light. And at the bottom here, the magnetic field lines are drawn here, so blue pointing downwards and red pointing upwards. These are the magnetic field, the B, in response to some applied light. And the point is that if you would like to get whatever conductivity matrix sigma you like, all you have to do is build a mesh of these circuit boards with the property that when light comes in, the current that flows in these loops gives you this sort of back reaction, if you will, the generated E and B fields, which has the effect of generating the sigma that you want. So this is the complicated engineering challenge to build the circuit boards that do this, but it actually has been done. Let me just show you a picture for my final slide of what they did. So this was a paper I sent out last week, but these guys did a proof of concept where they did this to basically cloak this copper cylinder from microwave radiation. So not visible light. This was just like, they throw microwaves at this and ask, is this thing invisible to an object that detects microwaves? Or said differently, would this object be invisible to some living creature whose eyes saw microwave radiation instead of visible radiation? And to do that, all they did was build this circular cloak. So I've circled it down here. The circular cloak is just like this thin shell or ring, if you will, built out of those split ring resonators. So that's shown up here. This enlarged picture is like a cutaway of a bunch of circuit boards with those split ring resonators arranged in a particular way to generate that sigma that we need. And then they tested, and I mean, they did a very good job, and this paper has thousands of citations, even though it was only from about 10 years ago. They tested that if you apply a microwave source to this copper cylinder hidden within this cloak made out of circuit boards, split ring resonators, that outside of the cloak on the right side, the sort of microwave radiation that you see is totally indistinguishable from if this thing had not been there at all. So it looks totally as though the microwave source sort of had just propagated through empty space. So you could not have told that the cylinder was there. So good, that's the punchline. So the whole point of this story was that you use some math, this coordinate transformation, to tell you what sigma has to be. Then with these split ring resonators, you build an object with that sigma, and that makes a cloak. And this has been done in practice, and there's some promising progress towards extending with the work that they did there for microwave frequencies towards visible radiation, which would be very exciting. I mean, the government is interested in this for obvious reasons, because the military would love to be able to cloak fighter jets and things like that from radar, and there's many, many applications you can think of. But those are outside of my area of expertise, so I will not talk about those. Good. That's all I've got. Questions or death threats?
I have neither. I do have a comment. Oh boy.
Is oh boy to be interpreted as like a positive comment or a negative comment?
I think it's interpreted... Yes, I am confused, and you said that is the correct... Wait, did I say amused?
You said
No, you said confused.
Okay. Well, now I'm confused, clearly.
Yeah, confusion is good, but I mean, hopefully the black box is good, right? You use equations of electromagnetism, you get some sigma, you build it, it works, right?
Confucian.
Oh, that's fine.
Confucianism. Lovely.
That's a different thing. Other comments? I guess I should stop recording now.